Okay, so we've been talking about point-free topology and constructive mathematics. I think we will start by kind of going over some of the things we did at the end of last lecture again briefly. I guess if there are any particular questions anyone has, I mean, I will go through this again, but otherwise, if there are any more general questions anyone has, I'm happy to answer them now. But otherwise, we'll get back into it. Okay, so I was saying how classically we have exactly two truth values, true and false. Constructively, it's a little harder to say, right? It's not true that we have three truth values. That's what we saw. But it's also not really true that it's not true that the truth values are either true or false. So it's one of this kind of subtle conditions. And what I was trying to explain last time, which maybe I can do more successfully this time, is that there's a distinction between what happens when you're actually reasoning constructively and when you're looking at some kind of model of constructive mathematics. So last time we saw this model of constructive mathematics, which was this idea of local truth. And in that concept of local truth, we said that we have, say, some topological space, and our truth values correspond to open sets in that topological space. And so you might say, oh, there are tons of truth values, right? There's one for every open set of this topological space we had. But when you're actually reasoning, that's what happens on the outside. So if we want to talk about opens of a topological space, we can talk about that, say, using classical logic or something. And that's how you can reason about these subsets of a topological space as subsets. But when we want to treat that model using constructive logic, we're now like in the universe where the truth values are the open sets of the topological space. And in this universe, everything is interpreted in these terms. And when you reason internally, you kind of want to reason not as if you're talking about opens of a topological space. You just want to reason using logic in a more familiar way. That's kind of the point of doing this constructively. And in this setting, when we kind of working constructively, and this is like the model we're doing, things don't work like that. Because if you take some open which is not the whole space and not empty, you might think it's like an intermediate truth value. But now when you check, is this equal to true, like the thing that's open, that's true everywhere, then it's not going to, like externally, it's not equal to true, right? Because it's not the entire space. But internally, it's equal to true on the region where they overlap. So if you have an entire topological space, and then you have some open U, you can say, in this region, this is equal to true. So it's not equal to true. It is equal to true to some degree. And essentially, this is why, if you say this is not equal to true, that's saying like, look at the region where it's not equal to true, and there it is false. That's kind of the idea. So this is why you can't actually, when we're reasoning in the constructive logic, you don't get an additional truth value. So hopefully that makes some sense.
It does make sense, but isn't it better to, because you like the topological space is not modeling the truth values. Like a point in the topological space is not a truth value. It's a sentence which is true. So for example, if I say cats are black is my sentence, then we have the collection of models where cats are black would be a subset of the universe. That's the open set that you're talking about.
Yeah, I guess
so it's not that we've got infinitely many truth values all of a sudden. It's rather the set of points where that particular statement is true, and then it's a very down to earth thing. It's not some weird thing.
Yeah. So for truth value, what like truth values mean? What I mean by it is, I mean take all possible propositions you could talk about, yes, and then quotient them so that logically equivalent propositions we identify. And this equivalence class of all these propositions, that's what I'm calling a truth value.
Okay, I agree with that.
Yeah.
But it's just okay, I agree with that.
Yeah. So So also, I think I mentioned this briefly last time, where this kind of thing, this lattice of truth values, the other way you can think about this is you can think of this as the power set of the one element set. So this omega, if you want, think about it as the power set of the one element set. So all the subsets of the one element set. So that's another way you can think about it. So classically, it's either empty or it's the entire thing. Constructively, it's a bit more subtle, but we can still talk about the power set of the one element set. And if we have any set, what we can do is we can map into omega, and this defines a subset, all the things that map to true. And on the other hand, if we have a subset, we can define a map into omega that says map every element to the degree to which it lies in S. And it turns out these are kind of inverses to each other. So there's a bijection between these two things. So we can say that omega to the x is the power set of x. So just like classically you'd say 2 to the x, we can kind of identify that with the power set of x. Constructively, we don't use 2 to the x, but we use this omega to the x, and it gives the power set of x. Okay. So
you just want to explain how the subsets of, or the power set of 1 corresponds to the truth values, like how.
Yeah. So at least in this case, so I say omega to the x is like the power set of x. So omega to the 1 would be the power set of 1, right? So in exactly this way, if you have maps from 1 to omega, okay, this is just the elements of omega, and then this is going to be the subsets of 1.
But the point is the elements are like, it contains the point, and then if you do like set comprehension with like the truth values that you.
Yeah. Oh, that's a good thing. So I guess in terms of notation, firstly, notice I use these funny square brackets, and I'm saying like this is the truth value associated with this particular proposition. So this is the proposition x element of S. I'm using these weird square brackets for the truth value. And then another thing which we will be seeing later that Peter mentioned is that there's this notation that sometimes we see constructively that we don't see classically, is you could have the set 1, the subset of the one element set. So the set of, if we say star is the set of the one element set, such that P holds, some proposition holds. And this is like normal set builder notation. But this proposition might not depend on star in any way, which is kind of unusual from a classical point of view, because what's the point? Because if P was false, we just say the empty set. If P was true, we would just say the set containing star. But constructively, sometimes it's interesting to consider the set of star such that some proposition P holds. That doesn't depend on star, because this proposition might be more interesting than just being false or just being true. So that is sometimes notation we end up using. And this allows us, and so this is the subset. For every kind of truth value P, we can have a subset of 1 corresponding to star such that P holds. So this is how you get all these weird subsets of 1. Okay. So before I was talking about how this set omega is a lattice. So remember, it's ordered by like logical implication. But it's actually a frame. It's not just a lattice. So in order to see that it's a frame, we first need to see that it has arbitrary joins, not just finite joins. So remember, I said finite joins are given just by disjunctions. But what about an arbitrary join? And so this is, I think this is quite instructive, seeing that this is the join, but it'll feel a bit strange, just like if you're doing an introduction to proofs course, where it feels like everything you're proving is trivial. But I thought it would be good to show why this is true. So if we have a join, some arbitrary subset of S, we want to construct the join, so that's the least upper bound. And I say this join is the degree to which T is an element of S. Okay, so how do we prove this? So we prove this. Okay, so we want to show it's the least upper bound. So first we want to show that it is an upper bound, right? So what does that mean? We want to show that for all elements in S, S is less than or equal to this thing. So we want that for all S and S, S is less than or equal to true as an S. But remember, this order is given by like logical implication. So so this is a lowercase s, right? So what we want to show is, if you think of this, we want to show that like s implies true as an s. But how do you prove an implication? Well, what you do is you assume that the hypothesis is true, and then you try and deduce the result. So let's do that. Well, let's assume that s is true. So s is true. And now we try and deduce the result. But if s is true, s was an element of s. So s was an element of s, and s is true. So true is an element of s. And thus we've proved this result. So this shows that this is actually an upper bound of this set. Okay. On the other hand, we want to show it's the least upper bound. So we consider another upper bound, u. So suppose u is an upper bound of s. And now we want to show that, so this is the least upper bound. We want to show this is smaller than u. So we want this is smaller than u. So again, we assume this and we prove this. So assume this is that's true as an s, and we want to show that u holds. Well, if true as an s, u is an upper bound, so u is an upper bound for everything in s. So that means true is less than or equal to u. But true is the largest element, right? So that means u is true, so u holds. So this actually shows that it's the least upper bound. So again, it feels somewhat strange when you aren't used to it, but hopefully this gives you some kind of idea of how you would prove things like this. Okay. Yes.
Sorry, Graham. So can you remind me, please, how did we get to gamma? Sorry, omega.
So you can think of omega as being the subsets of the
Okay, so
one element set.
We're not making it precise exactly what.
No, so I mean, yes. So if you're modeling this in a topos, it's a subobject classifier, right? But I'm trying to, yeah, it's just like we would talk about subsets of one or whatever classically, right? You can talk about subsets of one. There's certain axioms, right, that you can just discuss. You can form this object, and now we form this object, and we're trying to prove things about it, like that it's a complete lattice, for example. But yeah, I'm not being completely precise, but I'm being at least as precise as you would be if you're teaching kind of normal classical logic to people in undergrad, right? So I think, yeah, take it in this way. So it's a frame, but actually it's more than this. It's the initial frame. So I say it's a frame. Okay, I've shown you how to do arbitrary joins. So technically, you also need to show that finite meets distribute over these arbitrary joins, but this is easy, I mean, and less instructive than this one. So I think I'll leave you to check that. It's not difficult. But yeah, so it's actually the initial frame. And so what we want is we want to come up with a unique map from omega to any other frame. So this unique map needs to preserve joins in particular. And it needs to preserve one. It needs to preserve the top element of the frame. So we need to map 1 to 1. And now, but any element in omega, you can write as a certain join. So if P is like a truth value, you can write P as like the join of, say, true, such that P holds. So this is using one of these strange sub-singletons that we had before. So it's the join of true such that P holds. Again, from how joins work that I've just discussed, you can see that this is true. So this join needs to be preserved. So if we're going to map into an arbitrary frame, we need to map top to 1, and we need to preserve the join. So that means we need to map this to the join of 1 in the new frame such that P holds. So this is how we have to define our frame map. So this completely uniquely defines it. And then you can check that this preserves finite meets also. And well, check that it actually does preserve arbitrary joins and check that it preserves finite groups. So again, that's something you can check, but this is what you get. So this is in fact the initial frame.
So, sorry, can I ask it? So basically, are you telling us that we should imagine that we are in a certain logical system where truth values come from omega?
Yeah.
And now we'll be pretending that we're proving things and using that logical system.
Yeah, exactly.
And that's what's happening here.
Yeah, exactly.
But you're also telling us that it's nothing other than the initial object in the category of frame.
Yeah, it's the initial object in the category of frame. So classically, the initial object is like this two-element
category
lattice.
of frames in that logical system.
Yeah. No, well, the logical system is the entire world, right? No, you can. No. Yeah, I think you can forget about that. That's my point. So imagine the entire world is this. So it's just the category of frames, but we're just using constructive logic. Now, of course, if you want to apply it or something, you might sometimes want to take an outside view and stuff. Or in these models I was telling you about, before I was taking this like view from the outside. But now I think that the easiest way to think about it is now imagine you're on the inside. So we're taking for granted that constructive logic is the correct logic. We aren't doing classical logic anymore. We don't believe classical logic anymore. We're just kind of in the universe now, and you're just reasoning like we normally reason. That's kind of the point. Okay. So I told you that, so we know that frame homomorphisms correspond to, we know that morphisms into omega correspond to certain subsets, or correspond to all subsets. So if we have a frame homomorphism into omega, that's going to correspond to a certain subset of the frame. So, okay, so it's the initial frame, right? So we know there's a unique map from omega into any frame. But now if we want to look at maps out from L into omega, frame homomorphisms, these are going to be certain subsets. And it turns out when you check which subsets they are, by just doing the bijection, they correspond precisely to these completely prime filters that I mentioned before. So these are what we call the points of the frame. So maps from L into omega correspond to points. And this is really what we would expect, because if we work in lock where we turn all the arrows around, then this initial object becomes the terminal object. So a frame homomorphism from L into omega becomes a locale map from 1 into the locale. And we expect a map from 1 to give a point, right? So this really is, everything's working how we would expect, like from the categorical perspective, that we want points to correspond to maps from 1. Okay. Any questions? Good. So I do want to talk a little bit about the set that just contains false and true, because it's still interesting. So this is still something we can think about constructively, and it ends up being a subset of omega. Now, one thing that maybe is a little bit surprising, you might think, well, isn't this a frame? And why wouldn't this be the initial frame? That's something that I remember being confused there when I first saw this. And it turns out you can't prove that 2 is even complete constructively. So this 2-element lattice, you might think it's complete, but it's not necessarily complete. And one way to think about this is that, well, consider this join, right? What value is it supposed to be? It's supposed to somehow either be the top or the bottom, but it doesn't really seem like there's anything to do for it. So at least it's not obvious this is complete. And in fact, there's certain models of constructive mathematics where it's not complete. Okay, but this 2-element set is still interesting. So we can still consider 2 to the x. This is interesting. So this corresponds to maps from x to 2. And a map from x to 2, it's a subset of omega. 2 is a subset of omega. So a map from x to 2 is going to be a certain special subset of x. And these special subsets of x are called the decidable subsets. They're precisely the subsets where we can say either x is an S or x is not an S. So it's kind of a version of excluded middle that holds in this case. So you call such a subset decidable, and that's a map to 2. So this is still an interesting thing. We often care about decidable subsets. Decidable subsets will behave much more like how we expect things to behave from classical mathematics. So it's a good idea to have some kind of understanding of them. In kind of topological terms, you might think of decidable subsets as being analogous to clopen sets. So it and its complement, okay, are both these things we can talk about. or in a frame, this corresponds to a complemented element in the sense of lattice theory.
And why is it double element? The elements of elements.
Where is that? Maybe I made a mistake?
It says the elements of 2 to the power x.
Oh, that's probably just because I made a mistake. Yeah. So that's a kind of typo type thing, which I have given this talk many, many times, and I haven't noticed it ever. And okay.
So it's possible to make mistakes in constructive mathematics as well.
Yeah. So the other thing is, on the natural numbers, equality is a decidable relation. So what's a decidable relation? I mean, it's a relation when you view it as a subset of n cross n, it's a decidable subset. So for the natural numbers, or say the rational numbers, equality is decidable. And when you have a set where equality is decidable, they end up behaving much more like they do classically than other sets. So it's possible for a set to not have decidable equality, but for the natural numbers or the rationals, they always do. So that means for any two natural numbers, they're either equal or they're not equal. And this is useful. It means we can sometimes define things by cases for natural numbers in ways which we can't always do constructively. So this is a good thing to know. Also, I've mentioned equality, but it's also true for inequality of natural numbers or inequality of rationals. These are things which they're either less than or they aren't less than. Okay, so yeah, so it's new and it's kind of difficult to think about if you aren't used to it. So why are we bothering? I went through this a little bit before, but the point is, when we do this constructive mathematics, as I say, when we're doing it, we imagine we're in the world and everything's constructive. But then after you prove the result, you can take a step back and you can think, okay, what does this give us? And one thing it gives you is you can interpret it in all these different models. And so the models are given by different toposes. And then when you see what this result gives in these different models, you get a whole lot of different results. So when you interpret it in like the usual kind of topos of sets, if you have a classical meta theory, then this is just going to give the usual classical result. So by proving a constructive result, we get the classical result. Okay, great. But you also get these other things. So if you have G being some set, even if it's some kind of topological, G being a group, it can even be a topological group. Then this can correspond, you can get this topos of G sets, but in this topos, we don't necessarily have excluded middle, we don't necessarily have the axiom of choice, but we do have excluded middle. So we could have used excluded middle if we wanted to prove about these things, but we couldn't have used the axiom of choice. But if you prove it constructively, you haven't used the axiom of choice, so you can interpret it there. If you work in what's called the effective topos, that's the topos where everything's computable. There you're allowed to assume dependent choice, but if you prove it completely constructively, of course, then it also works. It'll be able to be interpreted there. If you have a certain topological space or a certain locale, B, you might want to consider the topos of sheaves over B. And it turns out that locales internal to this topos correspond to locales equipped with a morphism into the locale B. So when you prove things about locales in this topos, you end up getting results about like morphisms into B. So bundles over B kind of correspond to just being locales in this topos. So again, and there aren't really any normal classical principles that you can generally use in this setting. But if you prove results completely constructively, it'll be true here. So, and I'm saying, okay, so if you prove results about topology, in each case, we get the classical results in the first topos, we get G equivariant topology in the second case, we get computable analysis in the third, and we get 5-wise topology over B in the fourth case. So by interpreting these things in different toposes, we get a whole lot of different results, and all of these results come for free, or at least for the price of proving the results constructively to start with, rather than classically. So you can't use excluded middle, you can't use axiom of choice, but this is really the kind of the results is we get all of these additional results for free. The other thing I want to say, this is maybe somewhat more controversial, but I find when I'm proving things and I want to use excluded middle, I'm almost always making a mistake. So when I'm trying to prove a result and I think, it would really be easier to prove this result if I just take excluded middle at this point, 90% of the time, I'm actually doing something wrong. And I shouldn't have tried to use excluded middle. I should have just tried to prove it constructively. So I think, yeah, it's usually like good results tend to be true constructively, at least if you formulate them in the correct way. So if you formulate them with locales and things, so they should be true, and then the kind of extra constraints you have by trying to prove them constructively usually rules out all of these like bad ways that you could go about trying to prove it that aren't actually going to work. And I guess your mileage may vary, but that's what I find to be true. So I guess that's the kind of basic introduction to constructive things. That's the first half of our talk today. Are there any questions about what we've done? I mean, we're going to be doing more things later in the course, so hopefully as you see more and more, it will become reasonable, but yes.
Maybe you mentioned this already in the first lecture, but a nice, for me at least, a nice guiding example of truth values lattice is the 0-1 interval, where the truth value is probability of something being true. And that's an example of frame. Did you talk about that example?
So I mentioned a few kind of interpretations of constructive things. I did mention in some sense probabilities, but probabilities in the usual way of interpreting them don't quite work in this way. So like the kind of rules of probability theory aren't like the same as the rules of constructive mathematics, right? But certainly there are ways in which you can take this interval and you can, I did talk about this idea of like truth values being opens in a certain topological space as an example. So yeah, so there's certainly things like this.
Are you saying that sort of the logic of probability theory, the logic of probabilities doesn't match the logic?
Yeah, I'd say that when you're doing kind of, there's ways to think about probability theory as being a logic where the truth values are probabilities. But that logic, I don't think, it's not obviously intuitionistic logic.
Maybe, I'm not sure I follow that. I mean,
well,
just applying everything you do here, applying that to 0-1 interval.
Yeah, so you can do that. But I'm not sure that corresponds to probability theory. Like for example, when you're taking join, you're going to get when you have some event happens or some other event happens, usually like add together the probabilities if they're mutually exclusive. But in this kind of setting, what we're going to do is we're going to take the maximum of the probabilities type idea because we'd use the lattice structure. So it doesn't feel quite like probability theory. It feels like
okay, so there are some concepts maybe of probability theory that are not in a trivial correspondence with, but certainly probability theory makes use of this logic that probably has a bit more than that's not accounted for.
Yeah, I think probability you can view in logical terms, but it's a slightly different kind of logic if you want to get the kind of the way probabilities usually behave.
You can do sort of first order logic where the only difference is that you're using that interval instead of
exactly. Yeah, that's what I mean. Yeah. So I don't see why.
I guess I need to see the example and think about it.
I don't think there's a problem, but surely probability theory makes use of the fact that 0-1 is not just a lattice, but it's a linearly ordered set. So there's a bit more happening there than in general case.
Yeah, but I think it's really these extra logical operations that are more the thing that's maybe difficult to deal with. But yeah, there may be some way to view probability theory in this way, but I'm not completely convinced the most straightforward way works. But I guess we can talk about this maybe more later. Okay, but now I want to go into the topology part of the talk today, and that is presentations and classifying locales. So this is really what I think is. You can ignore constructive mathematics, and this is still true. I think this one of like the biggest advantages of the point-free approach to topology is the fact that frames are algebraic structures. So frames are just certain kinds of algebraic structures, and if you have an algebraic structure, you can present it with generators and relations. Just like if you have a group, you can have a group presentation where you give generators and you give relations, and you can construct a group kind of satisfying certain properties. We can do the exact same thing for frames. And this ends up being like very, very useful. So just to tell you what a presentation is, so we write it in this way with these angle brackets. And here G we say is a set of generators. So G is just some set, but we call it the set of generators. And then R is a set of kind of equalities between formal expressions built out of G. And we call this a set of relations. So I'll give some examples soon. But the idea is what this will give is it'll give us like the freest possible frame generated by G, subject to the conditions that the relations impose. So kind of more formally what I'm saying is if you have a frame homomorphism from this frame given by this presentation to a general frame L, frame homomorphisms out of this presentation are going to be in bijection with functions that assign the generators to elements of L, such that the images of the generators satisfy the relations that we have. So this is generally how presentations work, but yeah, so kind of being able to talk about maps out of these presented frames is very easy. That's kind of the idea. Okay, so just to give you an example, so suppose we have a presentation where we have countably infinitely many generators, G1, G2, and so on. And then we have these, I just chose random relations. So we have G1 meet G2 must be less than or equal to G3. And G4 should be less than or equal to this join of all the GIs for I greater than or equal to 5. Okay, that's just a random thing I chose for illustrative purposes. And above I said the relations are supposed to be equalities, but here I've used inequalities. But it turns out it doesn't matter, because whenever we have an inequality in a frame, we can express it as an equality by saying whenever we say A is less than or equal to B, we say that A meet B equals B. So whether I use inequalities or equalities, it doesn't really matter either way. But I think one thing that's interesting to think about is what are the points of such a frame? So I've given you a random presentation of a random frame. What are its points? And remember, I told you that a point of a frame is a frame homomorphism into omega. So, but if it's a frame homomorphism into omega, we can use the universal property of the presentation. So we just need to say where every generator gets sent. And we need to check that these generators must satisfy certain relations in omega. So what are these relations in omega? Well, again, you can think of the frame homomorphisms. Remember, they're determined by what gets sent to 1, because that's how we go from maps into omega to subsets. We can just say what gets sent to 1. And these, so we just need to think about these as sets of generators. So we have a map from every element into omega, and then we can say, when do the generators get set to 1? And we have the set of generators that get set to 1. And these relations, so the relation that says G1 meet G2 is less than or equal to G3, when we interpret this in omega, it says that if G1 is in the set and G2 is in the set, then it implies that G3 is in the set. And similarly for this other inequality, it says that if G4 is in the set, then there exists an I greater than or equal to 5 such that GI is in the set. So you can take these relations and kind of give them this logical interpretation by just taking the operations in omega. So are there any questions about that? Does that kind of make sense? So we use the universal property. The universal property says that we just need to say what happens to the generators. So the generators map to certain elements of omega. But by this correspondence between maps into omega and subsets, we're saying we're taking the subset of generators that map to true in omega. And now they need to satisfy these relations. So if G1 maps to true and G2 maps to true, and G1 meet G2 is less than G3, G3 better map to true, right? So we get the first relation. And then the second one that says if G4 maps to true, then we need the join of these GIs mapping to true. But if the join of some things is true, that means one of them is true. Like that's one way of understanding the way I define join in omega. So so this means that there exists an I such that this holds. So hopefully that makes some kind of sense. But the point is that if you have a presentation, it's very easy to see what the points are. And in fact, you can turn this around and say that you can think of the presentation as actually defining what the points are. So here we can say the points are these subsets of the natural numbers satisfying these conditions. So these kind of logical conditions we've now expressed as kind of in frame language. And you can think of this as defining some kind of theory. And that's actually what we have on this next slide. So the presentation you can think of as defining what's called a geometric theory. So we spoke about geometric logic last week. And so we can have certain basic propositions, we can have certain axioms, and you can imagine kind of defining some kind of theory in geometric logic. So the generators are these basic propositions, the relations are the axioms. And also, we kind of spoke a little bit last week about how points somehow correspond to models. So points are going to be models of this theory. So the model will tell us which of the kind of propositions actually are true. But what's interesting is that in geometric logic, if you think about the models, just tell you the points. But the presentation of the frame doesn't just tell you the points of the frame, it also tells you the topology, right? So it tells you more than just the points, it also tells you the topology. So this is like really nice that if we define the points geometrically, so using this weak logic, it doesn't only give us what the points are, it doesn't only tell us what satisfies us, it also gives us a topology. And in fact, it works even if there aren't enough points, but we'll get there later.
Sorry, are you saying that the frame we get will be frame of open sets?
Yeah, the frame will be the frame of open sets, yeah. So let's see an example. I think this is best seen by considering an example. So our first and kind of most detailed example will be the locale of real numbers. So we want to define a locale of real numbers, and my point is, think about how you define a real number and just do it geometrically. That's the idea. So let's see how this works. So usually when we define the real numbers, we do it with Dedekind cuts. So let's try to remember what that means. So, okay, so if you remember what a Dedekind cut is, it's going to be two pairs. It's going to be a pair of sets of rational numbers. And the first element of the pair, you think it's the set of like rational numbers which are smaller than the real, so the lower bounds. And the second set is going to be the set of rationals which are larger than the real. So this is how we're defining the reals in these two sets of rational numbers. And they need to satisfy certain axioms. So you kind of arbitrary sets of rational numbers. So the first one is that if this is what we're thinking about, we want that the set L must be downwards closed, because if you have a lower bound, anything smaller is also going to be a lower bound. So that's the first axiom we want for L. The next axiom is that L is rounded. So it must really be things that are strictly less than a certain real, which means that if we have some lower bound, some rational lower bound of our real, and it's like strictly less than it, we should be able to go a little bit larger and still be strictly less than it. That's kind of how we imagine the reals would work. So we say that L is rounded. So for any element in L, there's an element that's a little bit larger than it. Okay. Finally, we say that there must be some element of L. We say that L is inhabited. So there must be some element in L because we aren't expecting this to have no lower bounds. That would be like the real is negative infinity. But we're wanting the reals. We aren't wanting the extended reals. So we require that, we want to rule that out. So we said that there must be some element of L. Okay. And then you can do similar things for U. So U should be upwards closed. U should be rounded. U should be inhabited. Okay, exactly, dual. Okay. Then there's this axiom that relates L and U. And essentially, you could think of it as saying that they're disjoint. So if we have something in L and something in U, then the thing in L must be smaller than the thing in U, right? Because the lower bound for a real must be smaller than an upper bound for the real. Again, this is kind of intuitive. And then the final axiom is locatedness. So this is maybe the most interesting one. It says if we ever have two rationals, and P is less than Q, then either P is a lower bound or Q is an upper bound. So if we just think in cases for a second, okay, they could both be above the real, and then the upper bound's an upper bound. They could both be less, and then the lower bound's a lower bound. Or they could span the real, and then, okay, both of them. One's a lower bound and one's an upper bound.
This corresponds to irrational numbers.
No, it corresponds to all real numbers. Because even if you have, because it's strict equality. So even if you have a rational, it's still whenever you have two rationals, like.
Oh, yeah, sorry.
Yeah. Okay. Cool. So this is the definition of reals by Dedekind cuts. But this actually is a geometric theory secretly. So how do we see this? So when we say that Q is an element of L, so some rational Q is an element of L, this is, we can think of as a basic proposition. So we give this a name, LQ. So LQ is the basic proposition, which we're thinking of as meaning Q is an element of L, Q is a lower bound. And then you also have a basic proposition UQ, which says that Q is an upper bound. And now we can rephrase all of these conditions in terms of LQ and UQ and see what we get. So the first one says if P is less than or equal to Q and Q is an L, then P is an L. So, okay, so first I'm writing the fancy geometric logic way. So when I do this weird turnstile symbol, just think that means implies. So it means that if LQ is true, then LP is true. So this is like an implication. We don't have implication in geometric logic, which is why I need to use this weird turnstile. But essentially, it's just saying that if the one's true, the other one must be true. So whenever P is less than or equal to Q, the method of the one implies the other. So in frame theoretic terms, in the relation, we just write LQ is less than or equal to LP, right? That means that LQ implies LP. Okay. The next one says, if P is an element of L and Q is an element of L, then Q is an element of L for some Q greater than P. So how do we do this? Well, we're saying if LP holds, then if you take the join over all Q greater than P, then some LQ should hold. And again, we can just write it with a less than or equal to, and we get what we need for a frame presentation. There is some Q and L. That means true implies that if you take the join over all LQ, one of them should hold. Okay, so that just means one is less than or equal to this join. And then you can do the same things for the upper bounds, right? Okay. So next, if P is an element of L and Q is an element of L, then P is less than Q. So in the logic, we can maybe write this like this. It says if we take the meat of P and the meat of Q, then it somehow corresponds to this truth value of Q being less than P. And it is possible to interpret this, but I'll tell you that it's actually simpler than that, because inequality in Q is decidable, right? So either Q is less than P or Q is greater than or equal to P. And if Q is less than P, then this is something implies true, which always holds. So we can throw that away. So we just need to consider the case that P is less than or equal to Q, and in that case, this is false. So we can say that this meat is less than or equal to 0 in the case that P is greater than or equal to Q. Okay. Any questions? Is that reasonable? And finally, locatedness. If P is less than Q, then either P is an element of L or Q is an element of U. So this says that when P is less than Q, okay, we have that LP or UQ. So again, we can write that as a generator. Okay, so I mean, I understand this is fairly quick, but it's just a straightforward translation, right? You just write down the axioms, and the point is that you can just go through and you can translate each of them, and you can get a relation for a frame. And in the end, we get a presentation. So this presentation, I claim, is the frame corresponding to the locale of reals. So usually in classical well, not in classical mathematics, in like point set topology or in kind of normal analysis, we first talk about the Dedekind cuts, we kind of define the points, and then later we'll go and define a topology, right? But this way, it shows it actually hidden in the definition of a Dedekind cut. It already knows the topology. The topology was there all along, because this gives you the reals with their normal topology. And these generators, the one I call LQ, it corresponds to this open interval, right? And this makes sense, because LQ means that Q is a lower bound for the real. So it corresponds to this interval of all the reals larger than Q. And UQ corresponds to the other interval, all the things smaller than Q. So we've obtained the entire locale of reals, and it's actually more than that, because constructively, this locale doesn't even have to be spatial. So it doesn't need to come from a space. So the points aren't necessarily the whole story. This actually gives you more than just the points. This is more information. I just want to say, if you think about the points of this, by construction, the points will be Dedekind cuts, right? We constructed, like by construction, we chose this so that when you work out the points of this, they precisely correspond to Dedekind cuts. We need to say for LQ and UQ, each of them are going to correspond to these sets of rational numbers. Well, rather, LQ is going to say Q is in the one set, and UQ is going to say that Q is in the other set. So by looking at all of them, by seeing which ones lie in the get back to 1, you can work out precisely what these two sets are. And then they must satisfy the axioms, which means actually these sets must form a Dedekind cut. So the point of this is precisely the reals, but again, this contains more information. So that was the reals, but we can also do Cantor space. So you need to think how you're going to view Cantor space. But here I'm thinking of it as an infinite sequence of bits, so 2 to the n. So we can now think from kind of our verifiability interpretation. We can say, what can we verify in an infinite stream of bits? Well, you can go to the nth bit, and you can say, is it 0 or is it 1? So if it's 0, you might call that generator Zn, and if it's 1, you might call the generator Un. And then, okay, if the nth bit is 1, it can't be 0, and if the nth bit is, but it's either 0 or 1, so you get these two axioms, and indeed, these give you the axioms of Cantor space. So when you work out the frame, you do get it with this presentation.
Sorry, what is the Cantor space?
So Cantor space, I'm just meaning, well, 2 to the n. So yeah, just the product of the 2-element discrete space with itself n times. Well, so like a count of the infinite number of times.
But then what are you doing with it?
So I'm saying we're going to come up with a presentation where there's a generator. The one generator essentially says the nth bit is 0. The other one says the nth bit is 1. Now, these can't both be true, so the mean of them must be 0. But one of them is true, so the join of them must be 1. And this gives you a presentation of a frame. And I'm claiming that the presentation of this frame is, in fact, the frame of opens of Cantor space. If you think about what the points correspond to,
how do we define opens? Sorry, it's a very childish question. How do we define opens of the Cantor space?
Yeah, the product topology. Yeah. I mean, yeah, classically, this is what you do. Yeah. But if you now work on what the points of these are, you can see that the points of these are going to be like these infinite sequences of zeros and ones, right? Because you need to take Zn for every n. You're going to need to say, does that hold or does that not hold? And Un, and that's going to tell you whether the nth bit is either 0 or is it 1. So when you actually work out maps from this frame into truth values, and they need to satisfy the axioms, it's going to tell you whether every bit is 0 or 1, and they can't be both 0 and they can't be both 0 and 1, and they must either be 0 or 1. So this actually defines the point corresponds precisely to an infinite sequence of zeros and ones. Does that make sense? Okay, good. Oh, the other way to think of it is points correspond to decidable subsets of it. So these are the subsets, remember, that have complements. So something's either in it or it's not in it. And so we've written it as 2 to the n, right? So maybe that's kind of instructive. 2 to the n is kind of the set of decidable subsets of n. So to see that, you can just say, which are the n such that so for a particular point, you can say, there's an open, like if you think of the kind of set of points that Un corresponds to, it's the set of points where the nth element is 1. And this is going to be some kind of, so it's going to say that 1 is an element of that decidable set. Okay. So here's a trivial example. Suppose we have a frame with one generator and no relations. Okay, so what does this give? Well, the points must correspond to truth values, right? Because a point is a frame homomorphism into omega. But to define such a frame homomorphism, we just say where the generators go. So the generator goes to an arbitrary element of omega. So that means the underlying space of this is omega. And then we have one kind of sub-basic open, which is the thing in omega that's true, that corresponds to G. And it turns out this is what's called Sierpinski space. So classically, Sierpinski space, it's got 2 points and like one non-trivial open, an open containing one of those points. Constructively, Sierpinski space, the underlying space is not the two-element set, it's the truth values. So this is what I said. And in general, if you just have generators and no relations, we're going to have maps from G into omega. So the points are going to be given by arbitrary subsets of G. So if you have a free frame on G generators, the points are going to be subsets of G. That's what they're going to correspond to. So this is Sierpinski to the G. Okay. Yeah, any questions about that? Okay. So then my final example for today is a strange one. So let's fix the set and let's make it inhabited. So inhabited is just saying it has some element. There's some element in the set. So classically, you'd say non-empty, but constructively, you want to be a bit more precise. So we say there's some element in the set. And suppose we have basic propositions, and I'm calling the basic proposition f of n equals x. So this is just a single proposition, but I'm writing it out like this so you know what it means, because what it's going to tell us is it's going to say we want to describe a function. And it's going to be a function from the natural numbers into x. And what this basic proposition tells us is that n gets mapped into x. So f of n is x. And what I want to actually describe is surjections from n to x. So how would we do this? So, well, firstly, if f of n is x and f of n is y, x better equal y, right? That's for it to be a function, right? It must have this uniqueness property. The second axiom says that, okay, so if we have a certain natural number, there must exist an x such that f of n equals x. So that's telling us that it must be left total as a relation, right? There must always, for any natural number, there must be something that it maps to. And the third axiom says that for any x, there must be an n that maps to it. So that's surjectivity. So these are the axioms that give us that it's going to be surjective functions from n to x. So the points you can check are precisely surjections from n to x. But now what we can do is we can take x really large, right? Take x to be the power set of n, right? Then there aren't any surjections, so that means there are no points. But this is still a non-trivial locale. So this is a locale. If you choose this x to be very large, it's a very interesting non-trivial locale, but it doesn't have any points. So how can we think about this? Well, one way you can think about it is you can say, locales, we're talking about what you can do by finite observations, but by finite observations, you can't necessarily tell that there aren't enough surjections because you only look at finitely many kind of values of the function. So who's to say whether it's a surjection or not? That's maybe some kind of vague intuition. The other thing is you can think about this in terms of forcing. So in terms of forcing, you can, if you have any set x, you can always make it countable. So if you force a set x to be countable, then, okay, then there are going to be points here. So this locale is kind of noticing the fact that even though there are no surjections from n to x, there could be a forcing extension. So that's some way you can think about it. So another way of saying this is there exists some toposes in which this locale does have points, but we just can't prove that it has points in this topos. So I guess, but what I want, so this is a weird example. It's kind of pathological, though it ends up being kind of important actually for certain things in topos theory. But I think this is, I just want to emphasize that we described this in terms of the points. We did this by axiomatizing the points, but it doesn't have enough points. So it's weird, but geometric logic allows you to do things like this. So I think that's all I have for today. Are there any questions, like general questions about presentations or anything I spoke about? Yeah.
So can any frame, well, I suppose the answer is yes, but maybe you could elaborate a bit. Any frame can serve as the frame of truth values, right?
I wouldn't say it like that.
Is it not true? So you showed us earlier that if omega is the frame of truth values and it's the initial object in the category of frames.
Yeah.
Yeah,
so in some sense it can't. What you're saying isn't true. I mean, what you're thinking is you're saying, if we have a notion of a frame externally, we can come up with a topos where the subobject classifier kind of corresponds to kind of that particular frame or something. And that's true, but that's where you're looking externally. Once we're in the world doing constructive mathematics, there's an initial frame, right? And that's the truth values.
Yes, but what I mean is more things the following. So we take any frame, we declare that to be the truth values of our logical system. And then the question is, what are the other frames in that logical system where that thing is initial?
Yeah, no. You can do that. This is like this idea of hating valued sets, right? So absolutely you can do that. I guess that's just not kind of the perspective that I'm thinking about. Yeah. So what you're saying is exactly true. You can use this to construct a universe for any frame where the truth values externally correspond.
What will be the other frames in that case?
Yeah. So this is this example. This is this example of what you're doing is it corresponds to this topos of sheaves over the original locale you started with. So what the frames correspond to is they correspond to frames equipped with frame more. This is initial, right? So they correspond to external frames, but equipped with a map from the thing you started with. So in terms of locales, it's a map from X to B. So this is a bundle over B.
Is it the comma category?
Yeah, exactly. Okay, good. Oh, wait, I guess we should check whether there are any questions online. Okay, there's a question of what top element of S means. So sorry that I didn't see this, but what I mean is when I'm taking these weird square brackets, they just mean what's the truth value of that. So is true an element of S? Okay. Oh, I see that we're actually a little bit over time, so sorry about that. But
is it possible to like see all the participants? Sorry, thanks. Okay, great.
Okay, good. But otherwise, I think since we're over time.
Hi, Graham. I have a question. I'm still on time.
Yes. Sorry. Let me turn up the volume because I can't hear you very well.
Do frames form something like an elementary topos or something like that?
So frames themselves don't form any kind of elementary topos or anything. But you can construct toposes from frames. So there's this topos of sheaves over a frame, and that forms a topos. Of course, the category of frames doesn't form a topos. Does that answer your question?
No, that for sure, but I was actually thinking about using the frame of truth values as like
like what Graham was
the
saying
classifier
before.
for frame.
Exactly. So there's a way to kind of construct a topos out of a frame. This corresponds to the topos of sheaves. It's the same as the topos of sheaves. But you can think of it in terms of this hating valued set approach, where the truth values really are the elements of the frame.
Yeah, I'll think more about it. Thank you very much.
Yeah, sure. Yeah, no, sure. And yeah, you're welcome to, we can talk about it later.
Yeah, sure. Thank you.
Okay, great.